Welcome to session 5 in the series Analog Circuit Design using ADS. Now here we are going to do some practical work because enough of theory in first 4 sessions. So we should see some little bit of practical work. So let's make a folder, call it device characteristics. Device characteristics, right? And then in that folder I'm going to make a schematic called NMOS characteristics, right? And to this there is a library attached, so there are certain library files here, right? So I'm going to use a BSIM4 model. So I'll go to devices MOS, okay, yeah, here it is, devices MOS, and the 8th row from the top is a BSIM4 component. So this is a BSIM4 NMOS. Right, now this process is called Silterra process. It's a 130 nanometer process, and the device, this is a triple tap process. That means that the NMOS device sits in 2 wells. That means that it has got, besides body terminal, it has also got, what is called a sub C or a sub bang, where you can connect this to VDD. So basically there is double level protection. Now this process is for memories like DRAMs, so that the leakage to the substrate should be very less. So that's why you have a triple tap process. An NMOS device is a 5-terminal device, but the way it is modeled in ADS is a 4-terminal device, where each device you can assume to be sitting in its own well, and you can safely connect the body terminal to the source. Okay, so that basically gets rid of what you call body effect. So we will talk about body effect later on, but assume that there is something called body effect. So when I do a little bit of more theory, you will come to know what is body effect. Now double click that, and I'm going to clear the display of all these quantities. I'm going to just display a model name. So in my case I have modeled this as NFET4. Okay, so I will name this as NFET4, and in my model is called NFET4, and the length of the devices I'm going to use is a 130 nanometer. That's the minimum gate length. Okay, so it can go from 130 nanometer to 350 nanometer, right? So as I talked, if you change the length, you can change the output resistance, right? So that's why I'm still going with the least one, and the width is, let's say, 2.5 micron per finger. So if there are 2 fingers with a multiplicity of 2, there are 2 fingers. Now I'm going to display only the important quantities here: the model, the length, the width of the finger, and the number of fingers. Right. So I don't see the model, length, width, number of fingers, right? So I can use F5 to move the. Another variable is called VDS. So in the same variable you can name 2 variables, VDS and VGS, and say add. So we have 2 variables with a default value of 1. Okay, now what I want to do is I want to do DC simulations on this. So I'll go to simulation DC and put in a DC here, and next thing I want is an include file. So there is an include file over here. Now I want to explain you that this is the PDK which I have generated, and I have fitted a model here, a BSIM4 model for this 130 nanometer process. So if I go inside, I have MOSFET models, right? So if I look at BSIM4 and FET4, so this is the NFET4 model. So I'll just show you what that is. So if I go here and say component options, so set all. Okay, so you see that there are lots of parameters here. So this is this bigger model, right? So there are lots of parameters here. So I have extracted these values and then I have filled in there. Not only that, there are certain skew parameters which are for process variations. So if there is these are skew parameters, right? So if I go here, so these are my across process variations, right? Statistical variations. So those parameters are going to have these equations which use those coefficients which are over here. So this process will allow you to do Monte Carlo and other kind of yield analysis, because you can look at across process variations. So I'm going to just undo it. Just for your information, I was telling you that that's what happens inside a process design kit in ADS. You take a model and you fit it, and then basically you can use that model. Okay, so I am going to do that. So that model is placed. That's why it's called NFET4. Once this is done, I'm going to also do a sweep. So I'm going to sweep a VDS from 0 to, let's say, 2.4 volts. Okay, so let me tell you, there are two threshold devices here. Okay, one is a smaller threshold device which is used for high speed applications. Okay, and this is also a 1.2 volt device. The nominal supply voltage is expected to be 1.2 to 1.8, but the device drain source junction breaks down around 2.2 volts. So you can use this up to 1.8 volts as a supply. Okay, so I'm going to sweep this up to 2.4 volts in steps of 0.01, 0.001 if you want. So these many steps are there. So this is for VDS. Now I can also display this by saying variable to sweep and start, stop, and step frequencies. Step variables. So I'm sweeping VDS. Now I want to sweep is one more parameter, which is VGS. The threshold of the device is roughly around 0.2 volts. So I am going to put in a parameter sweep here, and this parameter sweep is going to be sweeping VGS. And VGS, I'm going to go from the turn on voltage, which is 0.2 volts, to let's say 0.8 volts. Okay, in steps of 0.1 volts. So that's around seven graphs or 7 curves I have. 0.1 volts, right? Sorry. Okay, so 7 curves are there. So okay, now if you want to do a nested sweep like this, you have to have the outer loop tell where is the inner loop. The inner loop resides inside DC1, so you have to mention that. So the inner loop resides inside DC1. So we are set to do this simulation, right? So let's just hit simulate. Okay, don't worry. Okay, just close this. So just run this again if it's required. Don't show this, run away. Okay, so once the simulation is complete, it will come up with a data display window. All you have to do is plot the current, and this will be the output characteristics which I'm trying to plot, right? Okay, so if I plot the current, so this is what we derived also, if you remember. Okay, if you remember what we were doing in session 4, we are seeing here. Now if you remember one more thing, the slope over here, okay, so this slope is going to be half the slope into saturation. So if you were to be here, so now you can see what I was talking about. So you see here, this is the slope here, and that's the slope over there, right? So if you are at the pinch off, so these are all pinch off points. So if you are at the pinch off, you are going to see smaller resistance, while if you are well within saturation, you are going to see larger resistance. Okay, one more thing is there. That thing is as follows. Okay. The other thing which I am mentioning is, if you see these steps, right, they go with the square. Okay, where is the square law nature? That square law nature is like this. You join all the points which are basically what you call, okay, so if you join all these points, okay, so you have that square law nature. Okay, so this region on the left side of this, right, on the left side of this region is known as the triode region. This region is the saturation region. And then if I consider a region far beyond, the current will take off. Okay, so that region would be called the breakdown region, right? So we are supposed to operate the device in this region, right? This saturation region. While we are, if you want to use a MOSFET as a resistor, for example, then you can use uh, in this linear region, which is close here. It's linear, and if you go further, it will be a square law nature, and if you go further, it will be a linear nature due to channel length modulation, and if you go in this region, it is going to be the drain to bulk junction breaking down. Okay, so we are supposed to be operating here. Okay, so once this is out of the way, what can I do from this curve? I can find out the slope. So to find the slope, I will just place two resistances, two markers. Okay, so there are two markers here, M1 and M2, and I can say RDS will be the inverse of the slope. RDS would be equal to independent of something divided by something. So in this case, independent of marker, right? So I can say INDEP of M2 minus INDEP of M1 minus INDEP of M1. So this is how much I have traveled in the x-axis. Then if I do M2 minus M1, this is how much I have traveled in the y-axis. Okay, so this slope basically is going to be the output resistance if I am on this curve. And if I want to display this, if I double click it and say go to display label, so it will display the various values of the gate to source voltage for which these curves are. So if VGS equal to 0.7, then the resistance RDS, okay, so the resistance RDS is, okay, let me just get rid of some things which are injuring, is equal to 6.037 kilo ohm. Okay, so this is RDS. Now if I was to move to a lower curve for same drain to source voltage, right, now it has increased to 8 kilo ohm. If I still go down, so if I reduce the current or reduce the overdrive, now it is 12 kilo ohm, and so on. Now if, for example, I was to take this length, okay, which is 130, and make this as twice, which is 260, okay, and also I am going to make the width to be 4 times, okay, so I am going to expect much higher RDS. Okay, so now the same thing which was 12 has now become 30 kilo ohm, right? So if you keep going up, it will keep on reducing. This is 17 kilo ohm here. This, what was 6 kilo ohm, is now 12 kilo ohm, right? So L, basically increasing the L is going to increase the output resistance. By W by L ratio is remaining the constant. So the currents are going to remain constant. It's just that the slope is going to change. So if you want a higher resistance, higher output resistance, you can take L up by a factor, but also you can take W up by the same factor. So W by L is a constant, and the drain current mu n C x by 2 W by L into VGS minus VT overdrive, V overdrive square, right? That is a constant because WL has remained constant. Okay, you bump up W and L by same factor, so their ratio is the same. So the currents are going to remain the same, but increasing the L would increase the output resistance, as we have just seen here. So that proves our point. Now let's look at the transfer characteristics. For transfer characteristics, what I'm going to do is I'm going to change the data set. I'm going to change the data set to 1, and then I'm going to swap the roles. Here I'm going to sweep VDS. Oh, sorry, here I'm going to sweep VDS, and VDS I'm going to sweep from 1.8 volts to, let's say, 2.4 volts, 2.4 volts, right? And steps of 0.1. So there are 7 curves again here. So this is VDS. So the outer loop is VDS, the inner loop is VGS, and I'm going from 0 to 2.4 in steps of that. So that is VGS. Apply, and if I hit simulate, okay, now I'm going to plot here from the different data set. So I'm going to go and use this data set and plot IDS. So here, this is your transfer characteristics, and what do you see? You see that there is a threshold. Threshold is around 0.2, okay, but then there is a sub-threshold leakage here. Now this curve won't make a lot of sense unless you look it in a log scale. Okay, so here there is a sub-threshold current, okay, and then you are going to have weak inversion, strong inversion, and in a strong inversion you will also see that this bends down. Okay, so I want to show you that. Okay, the reason for that is mobility degradation. So we will come to short channel effects later on, but for now this is the transfer characteristics. So from there, what do you get? Okay, so if I put a marker here, okay, so this is on VDS of 1.8, and if I put a new marker here, this is a VGS on 1.8 volt curve. So basically I have got, sorry, VDS equal to 1.8 and then VGS, right? So this curve. So if I find the slope of this, that will be the GM of the device. So if I go to GM, I can write an equation for GM. GM will be equal to something divided by something. Okay, so this something is going to be M2 M3 minus M4 minus M3. Okay, M4 minus M3 minus M3, and here it will be independent of INDEP of M4 minus INDEP of M3. Okay, so once that is done, this is the GM of the device. So I can just copy this and put it here and call this as GM. Okay, so the GM of the device is 5.27 milliamperes per volt. Okay, so that's the GM of the device. Okay, so I have what you call the output characteristics. Sorry, output characteristics, which is over here, and I have got the transfer characteristics, which is over here. Okay, so we have output characteristics and transfer characteristics. From one side we get RDS, from the other graph we get the GM of the device. Okay, so this is very simple. Now same setup if you want to do for a PMOS, the polarities are going to be different, because here in PMOS the carriers are going to be the holes. Okay, so if carriers are holes, then the source has to be at a higher potential and the drain has to be at lower potential. Similarly, gate has to be at a lower potential than the source. So it will be connected opposite. Okay, so I'm going to set up the same thing for PMOS characteristics. Okay, same size device. So in this case I am going to turn it back. No, I'm going to leave it this way. Okay, that's okay. So this is for a device which is a 260 nanometer, right? Okay, I'm going to take the same device. I can just do a control C or copy, and I can make a new what you call, I'm going to make a new schematic, and I will call this as PMOS characteristics. Okay, so in this case of PMOS characteristics, I'm going to just paste that device, and I am going to flip this device because I want the source to be up. And this is an NMOS. I'm going to change this to PMOS by just renaming it. Rest of the quantities remain the same. I will call this as a PFET, right? And all I'll do is I'm going to just display what I want to display, which is the model name, the length, the width, and the multiplicity. Okay, so F5 over here. Okay, let me make sure, yeah, I'm recording. Okay, fine. So in this case, again, the device sits in its well. I can connect the body to the source, and the way I'm going to connect this time is I am going to have two sources frequency domain. Okay, one will be VGS, other will be VDS, but here I will do this way, that this is 2.4, and this one is V 2.4 minus VGS, 2.4 minus VGS. Okay, and then the other one will be 2.4 minus VDS. Okay, and then I'm going to have a probe, and the anticipated direction of current will be out of the drain. So I'll go to the probe components, right, rotate it out, place it over here, and name this as IDS. So all the currents are going to be now negative, if you see. Okay, now all I need is the include file, and I need what you call include file, and I need DC, because I am doing DC analysis, so I need DC. So that's the DC here, and here I'm going to sweep VDS from 0 to 2.4 volts, 2.4 volts in steps of 0.1, 0.01 maybe, or maybe 0.001. That's okay. So as this goes from 0 to 2.4, the overall voltage VDS will go from 2.4 to 0. Is that there? Let's say 0. No, it will go from 0 to 2.4, correct. Now VGS I want to do in a different parameter sweep. So first of all, I'm going to display the sweep variable, start, stop, and step. Okay, next thing is I'm going to put a parameter sweep here. Again, the inner value of sweep is in DC1, so that's DC1, and I'm going to sweep VGS from, let's say, 0.2. So actually the turn on voltage for this is 0.35, so I will go from 0.3 to, let's say, 0.9 in steps of 0.1, in steps of, sorry about this, in steps of 0.1. So there will be still 7 curves, isn't it? Yeah, and say okay. So this is what I'm doing with the PMOS device, and I am going to just say simulate. Okay, what has happened here? PFET4. So let me put you on a hold for a second. The problem is you have used a variable which you haven't defined. So I'm going to go here to variable, and I'm going to define this variable. VGS has a default value of 1, and VDS has a default value of 1, 2, and then hit simulate again. So no errors now, and here we have the output characteristics. Okay, now one more thing, I'm going to rename this probe as IDS. Okay, so hit simulate again, and it will come out with a blank, so you just rename this to IDS, and we are oh, let's just put here IDS. Okay, so they are the curves. So now if you were to compare this with the curve from the NMOS, right? So let's choose an NMOS, and I'm going to compare this. I can put it on the same graph. So I take NMOS characteristics and look at its IDS. Okay, so you will see that this is almost 3 times. Okay, so this is almost 3 times the current in the PMOS. So that's why the factor of 3 comes in, because of the mobility. The mobility of holes is going to be 1/3 the mobility of electrons. That's why the current is 1/3. Okay, so this is that comparison. So if I'm going to delete this one. Okay, and similarly I can plot the output characteristics, transfer characteristics. So I'm going to go change the simulation setup, change the file name to be 1, apply, and here I'm going to sweep this. So I'm going to sweep here VDS, and VDS I want to take from 1 point, so the net voltage I want is 2.4, right? So hang on a second. So I can take it from 1.8 to 2.4. So the net voltage will be 0. So that's what I don't want, right? So I'll go from 1.6 to 1.6 to 2.2 volts. I can take 2.4 volts, 1.8 to 2.4 volts. That's okay, because it comes under a, so net would be 0 here, so that means it will be 2.4 over there. Okay, so there are 7 of them. Say okay, and over here I'm going to sweep VGS. Okay, so I'm going to sweep VGS from 0 to 2.4 volts. That's okay. So once I'm done with this, I can hit simulate and not change this. I am going to just place here IDS from a new data set, and that's that. So this is the transfer characteristics of a PMOS device. Okay, the turn-on voltage is going to be slightly higher, around 0.3 volts, and the GM would be smaller because, you know, mu p is smaller. Okay, similarly ID is smaller because mu p is smaller, 1/3 of mu n, or mobility, right? So this basically is a small exercise on NMOS and PMOS characteristics. Okay, so now I want to squeeze in one more topic here, because, you know, this will be not much for one lecture. So I'm going to talk about something called current mirrors. Okay, to do current mirrors, what do you have to do? First I have to explain you what is a current mirror. Okay, and I will explain you why current mirror as a load. Okay, so let's come to where I was explaining you in session 4. Okay, over here. Okay, so what happens is the following. Okay, if I was to draw the characteristics of a MOSFET, let's say NMOS or a PMOS, okay, what do I get? What I'm getting is some curve which is going to do like this, right? Or this is an exaggeration. Let's say some curve which is going to do like this. Even this I don't like. Sorry, some curve which is going to do like this and like this. That makes sense now. Let's expand this. Okay, so this is doing that. Now if I was to achieve this resistance here, so this is this slope. Okay, inverse of this slope is the resistance, because there is a current here IDS or ID. So there is a current here ID, right? So there is a current here ID, and then there is a voltage here VDS, right? Now this slope, okay, so let's say this slope is going to be your RDS, sorry, RDS is equal to 2 over lambda IDS, okay, 1 over 1 plus phi 0 divided by VDS minus V overdrive plus phi 0, entire thing in the bracket. If I was to achieve this resistance by simply a simple resistor, right? So if I was to use a simple resistor to achieve this, then this resistance is very large and it will start from here, right? So let's say these two are parallel lines. So this has the same resistance, but it will start from 0, because if you take resistance characteristics, if I equal to 0, V across it is 0. So you have to start from origin here. So when you start from origin here, the slope which you are trying to achieve is this, and the same slope you are going to achieve here, right? So the problem here is these resistances going to be very large, but then it will start from 0 volt drop across it. While in the case of MOSFET, the same resistance can be achieved with a smaller voltage offset, because I am not starting from origin. I am not starting from origin. Here the current is starting from origin. So to build up the same current, I would have to go a very long way before I build up the same current, correct? So in that case, the voltage across here will be IR, and that would take away the entire supply voltage VDD. So then you will be left with nothing across this device, which is going to act as a gain stage. So if there is a device which acts as a gain stage, right, and if I want to put a load which is equivalent by a resistance, then to achieve the same for a given current, to achieve the same resistance, right, I have to take the resistance to be very large, sorry, the current to be very large, and that, or rather to build up the same current, the voltage drop across the resistance would be very large, because we are starting from origin. In this case, we are not starting from origin. We are starting with a certain offset current and then building up this resistance. So these two resistances are the same, but in case of R, the net voltage across the resistor would be so large that it will swamp all VDD. While in case of MOSFET, okay, we start with the offset, not with the origin. So then we are just dealing with this slope here. Okay, so the resistance here would be higher. Okay, the voltage drop across the resistance, which is offered by a MOSFET, is much smaller than what would be offered by a physical resistor. That's why resistances are never used as loads. So if you see the BE degree, or the engineering degree undergrad, they put their resistive bias and all that. That's all nonsense, because you cannot design a circuit like that, right? So don't follow that course. If somebody puts a resistive load, really that course is not worth attending to that course. Okay, so you are going to use a MOSFET, not a so you are going to use a MOSFET for the reason that you don't have that kind of a supply voltage. Okay, so that clears basically why do I use a MOSFET versus a resistance as a load. Okay, I guess I'm clear why I use that VDS. Okay, because we start with the offset, we don't start with 0. That's the reason. Okay, so having said that, I have to come to current mirror loads. Okay, so if I take a PMOS device, okay, so if I take a PMOS device like this, okay, and this is the source, and if I connect the two PMOS devices like this, okay, and if I short this out here, so this is referred to as a diode connected transistor. Sorry. Oh, diode connected transistor. Okay, what is special about this diode connected transistor? The VGS is same as the VDS, which means VDS is same as, okay, so basically if I short this, so what is VGS? VGS is equal to VDS, VGS is equal to, or rather V overdrive. So let me write it down like this. V overdrive is equal to VGS minus VT, or VGS is equal to VT plus V overdrive. VGS is equal to VT plus V overdrive, correct? Now if I connect the drain source, so if I make this equal to VDS, then I'm guaranteeing that for any current the device is biased. So this is your overdrive voltage. So the device is always biased VT above V overdrive. So it is always in the saturation region. No matter if I reduce the current or increase the current, it will always be biased. If I reduce the current or if I increase the current, the device would always be biased VT above the V overdrive. So this is what this connection does. It places the transistor always in the saturation region, no matter what current you draw here. Now if you draw here a current which is very small, then see, overdrive voltage, okay, has a relationship with the current, right? So if I have a current ID divided by mu n COX by 2 W by L square root, that is V overdrive. Now if I make ID equal to 0, then V overdrive is 0. Then still the net voltage required across this is VT. Okay. Okay, so as long as we are above VT, okay, then this makes sure that VDS is VT above V overdrive, right? So having said that, this is a diode connected transistor, okay. So now what has happened here? What has happened here is this VGS1 is same as VGS2. If this is T1 and this is T2, then I have VGS1 is equal to VGS2, correct? That means that it is V overdrive 1 is equal to V overdrive 2, okay, because this is because I'm assuming that VT is matched for both the devices because they are the same process. So I can say VGS is equal to V overdrive plus VT, VGS equal to V overdrive plus VT, VT will cancel out, so V overdrive 1 equal to V overdrive 2. So what that it means is twice of, so this is the relationship, twice of ID, or rather let's say this current is IREF and this current is ID. So I can write this as twice of IREF divided by mu n COX by 2 W by L1 subscript 1 square root would be equal to square root twice of ID divided by mu n COX by 2 W by L2. Now if I was to square both the sides and cancel, I would say ID by IREF would be equal to W by L2 divided by W by L1. Okay, so when this is the story, then the current basically is mirrored with a ratio of their sizes. W by L is the size. So ID is this ratio of sizes multiplied by RF. So for example, if I do a 1:10, right, and if I have this left, IRF is equal to 5 microamperes, then ID is expected to be 50 microamperes because this is a 1:10 sizing. Okay, so this is called current mirror. Now this is an oversimplistic view. Now what happens is that current is, so when this IRF is IDS, IRF is IDS 1, which means that the device is operating at pinch off, right? Or I can say, okay, so I can say that this equation is correct when there is, so if you see ID is equal to mu n cox by 2 W by L times of 1 VGS, or rather V overdrive square, times of 1 plus lambda times of VDS minus V overdrive. Okay, so I'm assuming either the lambda equal to 0, then this equation holds, or the lambda is not equal to 0, but then the voltages are equal. So basically, if this node voltage is same as this node voltage, then this mirror ratio of 1:10 holds. If not, you are holding this to be constant and this V2 is varying, then it is just the device characteristics which you are going to see. So this current would become equal to this current when V2 is going to be equal to VGS1, right? Because the drain to source voltage over here is VGS1, so if, or VGS2. So this value of 1:10, for example, this mirror ratio holds, or the IRF to ID holds as a 1:10 ratio only when the voltage across the devices are the same, which means that it happens only at one voltage, which is V2 equal to VGS1. Okay, otherwise this doesn't hold good. Next thing is, it can also hold good if lambda is 0 or lambda is very close to 0. That means that if the impedance is very large. So if the impedance is large, whether the voltage, output voltage V2 is over here or V2 is over here doesn't make a difference, because the current difference is very large, because lambda is 0 or close to 0. So you understood that if you take current mirror, its output impedance is very important. Okay, so we will see what that current mirror does. Okay, so this is one current mirror. This is the simplest current mirror. So that's what we are going to implement here. So I am going to make another folder which I will call as current mirrors. Okay, and here I'm going to make a new schematic, simple PMOS mirror. Okay, so I'm going to make a simple PMOS mirror. So if I don't want to do a lot of feeding the numbers, I can copy this guy, edit, copy, and I can paste it over here, edit, paste. Okay, so now what I'm going to do here is I'm going to make this as 130 and 2.5 back to where it was, and then I'm going to make this one as 20, correct? And then I am going to just flip this device. So I'm going to make a copy of it, and so a copy of this, and I'm going to flip it like this. Okay, and I'm going to move the text here. Now I will just do the body terminal to the source because it sits in its well, body terminal to the source because it sits in the well, and connect them together like this, right? And this like this, and then this device is diode connected. So when this is diode connected, that does the job. Now the sources. So I'm going to go to sources, and this I'm going to keep as 2.4 volts. 2.4 volts. Let's see if I'm recording. Yes. So if I make this as 2.4 volts and connect it over here like this, correct? And then here I can pull out whatever current I want to. Let's say if I pull out 50 microamperes. 50 microamperes. Okay. And then I'm going to see what current I'm drawing here. So I am going to take in voltage here, V2. So that V2 is voltage. Okay, so that V2, what happened here? Okay, so that V2, I'm going to observe the current flowing in. So I'm going to have a probe component. A probe component like this, rotate it, put it here, and this is IO. And this current is IRF. Okay, so IRF is 50 microamperes, and this is a 1:10 ratio. So if I make this as a 2, Okay, so 2:20 is 1:10 ratio. Then at a certain voltage, which is going to be the voltage across this device is going to have 10 times the current, which is 500 microamperes. So it has mirrored your current. Okay, so let's just put here the PDK file, and let's declare a variable V2. And I'm going to save V2. Okay, so I'm going to go and put a DC simulation, and in this DC simulation I'm going to sweep V2, and V2 I'm going to go from 0 to 2.2. Caps lock is on. Okay, I'm going to go from 0 to 2.0 to 2.4 volts. 2.4 volts. Okay, now this is going to come out to be reverse, right? I can always do 2.4 minus V2, right? So then we will be going along with the 1. Okay, so here I can do 2.4 minus V2. 2.4 minus V2, and all you're going to see is the output characteristics of this device. Okay, so if I do here, say, okay, so now if I sweep V2 like this, let me just display it. Okay, and I hit simulate. Okay, if I plot current IO, okay, so this IO is over here, and then if I plot IREF, which is 50 microamperes, right? So let's put in here a marker, new. Okay, so let's see where it becomes 50. Okay, so here, okay, it becomes 50 kind of over here. Okay, so this happens when we are VT above V overdrive. So here we have something called V overdrive. Okay, so this value is V overdrive. Okay, so here we have something called V overdrive, and we have placed this transistor VT above V overdrive. So somewhere over here. Okay, this is VT above V overdrive. So this one, this difference, okay, so this difference is basically your VT, and this first value, okay, so this is V overdrive here. V overdrive. So we are in a, so this value is V overdrive, and this value is VT plus V overdrive. V overdrive, VT plus V overdrive. V overdrive plus VT, and this is because of the diode connected transistor. Okay, so this is roughly going to be equal to 0.3, yeah, around 0.5, right? So it is 0.3, which is the VT of VTP, right? VTP is the threshold voltage for a PMOS device. So we are seeing a V overdrive, and then we are seeing VT plus V overdrive, where the two voltages, the voltage across this device is going to be same as the voltage across this device. At that point, the mirror ratio will hold, which is 1:10. So if it is 50 microampere over here, it will be 500 microampere over here. So this is 500 microampere. Okay, so you understood that that's the story. Now, if I could reduce the slope here, which means if I could increase the output resistance of the device, then I would be able to get that 500 everywhere, right? So if I can make it flat. So one way to make it flat is what is called source degeneration. So I'm going to put in a resistance here. So let's rotate this. So if I put one resistance here, and let's say this value is R. So let's say that this value is R here and R here. So it is symmetric, right? So nothing changes. Only thing is that the VDC is going to be different now. It will be V 2.4 minus IR. So that will be the supply to the two transistors. So if we have enough supply room, then this is allowed. So let's here declare another variable R, and we start with R equal to 50. Right, R equal to 50. And then we are going to put we're going to simulate this, right? So what I'm going to do is, instead of simulation, I'm going to do a tune on R. Okay, so I'm going to choose this R as a value. Now if I go here into the data display window, okay, so of course this value will go down, right? So now we are not talking about 500, we are talking about 400. Okay, but what you are going to observe is, if I sweep this R to, let's say, 5,000, sorry, 5,000. Okay, so you see what happens to the slope. So the current goes down. That's understood. But you see what happens to the slope. The slope basically goes down with this source degeneration. The output resistance goes down, right? So you understand what I'm saying, right? So what it means is that I can use this resistance, but the real problem is, here is, I am dealing with the physical IR loss. So I do not want to lose the voltage here. Because of this loss of voltage, I am not able to achieve the current, right? So I would say close, and I would not update it. Instead of this, I am going to do the following. I'm going to remove this, delete this. I'm going to just put a factor of X. Okay, so let's say this R is a X, or rather I'm going to delete R and add X. Okay, so I'm going to declare a variable X here, and X equal to 1, and X equal to 1, say add. Correct? Now I can multiply both by X. Okay, so if I go here, I can take this one and I can multiply by X here. So if I go here, say multiply by X and multiply by X. So remember, if I told earlier, I told you that if you scale both length and width by the same X factor, then the size of the device remains the same. So basically what I'm doing is, I'm keeping the size to be same, X and X. Okay, so I'm keeping the size to be the same, and then I'm going to tune on X. Okay, so now if you see the output, it's still going to show you 500, right? This is 500 here. So let's just adjust this. So roughly here 500, right? So this is 500 point. Now if I was to tune on X, which is a multiplication factor X, where I'm scaling the length, okay, and I'm going to go to 1.5, so you see that point doesn't move. You see, unlike the, okay, so unlike that case of what you call, unlike that case where we had a physical resistor, now I am working with X. You see, the slope keeps on reducing. You see, if you scale L and W same time, so basically if you increase L, the output resistance of the current mirror or the output device goes up, right? So now it has very little dependence on the output voltage. It is still going to mirror 1:10 roughly, right? So you understood, we have to increase the output resistance of the current mirror somehow, so that V2 has no bearing on the ratio 1:10. Okay, so one more way of doing this is, let's get rid of X again. So let's get rid of X. Okay, so we got rid of X. Now what I'm going to do is, I am going to do one more trick, and that trick is, I am going to take this and repeat it. So repeat it at the top like this. Okay, so once you repeat it at the top like this, So this is referred to as telescopic cascode current mirror. So you have a telescopic cascode current mirror like this. Now if I was to now simulate this, okay, so I'm going to have the same resistance placed over here, but then that resistance is not going to drop a lot of voltage, right? You remember I told you in here, what is the difference between resistance and a MOSFET? Is that MOSFET is going to provide same output resistance as the resistor, but without dropping much of the voltage across it. So that's what is happening over here. Okay, and if I simulate it, so you see here, once you hit roughly over here, you hit 500, but after this there is no bearing on this. But also notice that you have moved from here to here. So the net voltage on V2 cannot go below this. If it goes below this, then below this value, so what is that value? That value is twice of V overdrive plus Vt, twice of Vt, twice of V overdrive plus Vt, twice of V overdrive plus Vt. Now I'll tell you how that is. Let me see if it is correct. So the net voltage over here is V overdrive across this combination is twice of V overdrive plus Vt, and that has to be the voltage across this. Okay, so there is a voltage required here, twice of V overdrive plus Vt is the net voltage which is required for this 1:10 to hold. Okay, now if you can take the Vt out of this device, the top device, then you would have twice of V overdrive plus Vt. So basically you can bring this down by a small number. Okay, Control C, Control V. You can make this to do this by at over here, where instead of this you are going to see here twice of V overdrive, but then this Vt comes out here like this. Okay, so you got rid of one Vt which you are dropping across this device. This is by forcing this voltage here to be V overdrive voltage. How would you force that? If I take this device and repeat it, so I'm going to repeat the same device over here. Now what I will do is I will make this device as 1/4 the size. So instead of 2.5, I'll make it 1.25, and this one I'll make 1. So now this is 1/4 of this size, so this size is 5 and this is 1.25, so this is 1/4 the size. Then I'm going to draw the same current. Okay, so I'm going to draw the same current over here. So now once I have made 1/4 the size, okay, then I have changed the overdrive voltage to be 2 times. So overdrive voltage on this device is 2 times on other devices. So what does it mean? It means that if I connect this from here to, let's say, here, and if I connect this one from here to here, so I'm forcing here twice of V overdrive plus Vt, and V overdrive plus Vt goes out here, so I'm left with V overdrive here. So I'm forcing a voltage of V overdrive at the drain to source of this device rather than V overdrive plus Vt. But I had a price to pay. The price to pay is the following. Okay, you know that the slope, okay, the slope over here is going to be half the slope over here, right? Now you are forcing that device to be over here, then the output resistance is going to be Gm times Gm of the device, which is Gm of this device, right? Gm Ro, which is AV. Okay, so Gm RDS 1 times of RDS. So now in this case RDS is going to be almost half of RDS1. So RDS1 by 2. So the net resistance at the output is GM RDS1 square by 2. While in the other case, what was happening was it was GM RDS1 square. Okay, so that's the price you have paid by forcing V overdrive across here. So once you do that, and I'm going to change the data simulation settings, I'm going to change this to 1. Okay, apply. All I have made is that this device is 1/4. You can do the same thing by keeping the size to be same but drawing 4 times the current here. And if I hit simulate, okay, so I'm going to do this is I'm going to plot this from a different data set. Okay, so now you see, okay, what you have done is you have achieved the same thing. Okay, so what is the net voltage required over here is the voltage required over here is V overdrive, and voltage over here is V overdrive again. So we require basically twice of V overdrive plus VT. So that would be sufficient to make the output current to be 500 or 1:10 ratio. So let's see where you get 1:10 ratio. Okay, so almost here, almost as good as your simple PMOS current mirror. Okay, so you have gained this much, you have gained this much. Okay, so let's make this red colored. Okay, so you have gained this much of the swing on the output. So the V2 can go down to this value, V2 can go down to this value rather than V2 to be at this value. So you understand that you have gained this much of voltage across the device. The swing can be improved. So this is called wide swing cascode current mirror. Okay, the only limitation here is that V overdrive, okay, VT should be greater than V overdrive. Okay, so this is because of this connection, right? VT should be greater than V overdrive. So that's that connection, and usually VT is much greater than V overdrive, so this works. So this is called wide swing current mirror. Okay, so we have covered 3 or 4 variations, and the idea was to improve the output resistance so that the output current is a ratio 1:10 or whatever is the mirror ratio for a large range of output voltage. So that was the whole goal. Now once you have that, we can start using this as a load for your gain stages. So I'm going to stop here for now, right? And maybe I'll cover gain stages in the next session.